Okay. Good afternoon. This is September 22nd, 2005, TELE 1022, Fanshawe College, London, Ontario. Telecommunications. All right. First thing we're going to tackle is the supplement that I got for you. And it talks about the total harmonic distortion. All right. Where's my board? Here it is. See, here is our X and Y axes. And this is the time. And this is whatever the quantity that we're measuring on the y-axis. It could be voltage, So let's make it voltage here. And if we have a waveform displayed on this graph, it is a waveform displayed within the time domain because the x-axis is time. All right. As opposed to when we have x and y axes, and this will be the frequency domain. And here would be, well, it could be the dB, and let's say dBV. And we're going to have a little bit different type of display. So let's say here we're going to have a little spike that shows our fundamental frequency. Let's say it's 10 kilohertz. All right, so the second harmonic of that's also the fundamental frequency is the first harmonic. However, we don't call it the first harmonic, we're calling it the fundamental frequency, but it is the first harmonic. Then somewhere at around 20 kilohertz, I'm just going to put kilohertz here so I don't have to write the kilohertz every time. There's going to be 20 kilohertz, the second harmonic. Third harmonic would be 30 kilohertz, 40 kilohertz, and 50, and so on. So these will be the harmonics, which could be the integer multipliers or multiplications of the fundamental. So fundamental is 10 kilohertz, second is going to be 20 kilohertz, 30 kilohertz, 40, and so on. All right. Now, when we are dealing, let's say we have a time domain here, when we're dealing with pure sine wave, all right, pure sine wave, then these guys here really shouldn't exist. All right. Because it's a pure sine wave, and that's it. Now, in reality, they do exist mainly because of something that's called the non-linear or the inlinearity of the device. The device that the signal passes through, like for example, an amplifier or whatever it is, will have some imperfections and is going to maybe amplify certain things in a non-linear ways. And instead of reproducing the signal, it is going to produce signal of its own. It's going to be distorted signal by adding those harmonics. Now, look what happens when we add harmonics. I just found something. Where is it? Here. I just found something, additive synthesis of waveform generator. I just typed in Google adding harmonics or adding waveforms, and I found one of those. There's tons of it on the net. So let's say here we have a fundamental frequency. Here's the harmonic first harmonic. And we're going to, let's say, have a waveform like that. Okay, now if we add, let's say, forget the second harmonic, if we add the third harmonic, look what's going to happen. Things are going to start distorting. Okay, let's get the fifth harmonic. See, I'm just adding the odd harmonics, a little bit of fifth, a little bit of seventh, a little bit of ninth, and we have 11th here, so why not? Let's just bump it up a little. Look what happens. We just added odd harmonics. So third, fifth, seventh, ninth, and 11th. So look, this thing starts reminding a square wave. Okay? Something to remember. Look what happens if we start adding the even harmonics. Here, oh, look at that. You almost get a sawtooth coming here. Oops. Yeah. Fourth, sixth, eighth, and 10th. We're almost getting a triangle happening here. So even harmonics is going to give us a triangle, and odd harmonics is going to give us a square wave. But every time we add something, any kind of harmonic, then any kind of harmonic, then the waveform begins to be distorted. Okay. Okay. I just wanted to show you that. Now, so we're talking about harmonic distortion. Now, what happens if we have some sort of another spike here that is not within the harmonics? If we want to calculate the total harmonic distortion, we're just considering the harmonics. Everything else is going to be noise. This spike will not be considered as part of the harmonic distortion because nomen omen, which is Latin for the name describes the purpose, nomen omen, the harmonic distortion is distortion that involves the harmonics. Okay. All right, so here's my supplement here for you. Okay, so the concepts. THD stands for total harmonic distortions. And by the way, this is going to help you with the next lab we're going to do. This week, we're still doing the lab that we started last week. And the week after that, we're going to start with the next lab. And this is going to help you with that. So THD stands for total harmonic distortion, as opposed to THD plus N, which stands for THD, total harmonic distortion plus noise. So distortion, total harmonic distortion, this is what we're going to concentrate on. A little bit better. The distortion is caused by harmonics only, as opposed to the distortion caused by harmonics and noise, measured in n number of harmonics, whichever we're going to consider, whichever number of harmonics we're going to do. And so this is measuring in whatever number of harmonics, and the THD plus noise is measured over a bandwidth, over a specific frequency range. It is given to us, specified in either percentage or decibels. Same thing, percentage or decibels. The total harmonic distortion plus noise is useful in more or less audio applications, audio amplifiers, mixing boards, and so on. It's the inverse of SINAD, which is signal, noise, and distortion. If you want to know more, here is a link. All right. Now, what we're concentrating on is the THD, total harmonic distortion, and it's more common, more useful within the radio frequency RF applications. Now, if you want to express the THD, which is total harmonic distortion in percentage, here's the formula. THD in percentage equals square root of the power of the second harmonic, third harmonic, and whatever number of harmonics we're going to take it up to. Maybe we want to take it up to fifth harmonic or seventh harmonic, okay? Over the fundamental, the power of the fundamental frequency, take a square root, so sum of those divided by the power of the fundamental, and that's going to give us a fraction number, and if we multiply that by 100, it's going to give us the percentage number. It will have no unit except just a percentage because we are dividing power by power, so the units will cancel. And we're going to call this thing, for our purposes on this sheet, as Formula 1. Formula 1. Here's the explanation of things. Now, if we want to describe this, we want to have the expression in decibels. And decibels is not really a unit because it's a ratio also. Although some certain types of decibels, certain kinds of decibels could be actually considered a unit. Like, for example, dBm. It is a dB ratio with a reference to 1 milliwatt. All right, so that would be power. Or dBV, which we get displayed on our oscilloscopes when we turn on the FFT function. Then we get the results in dBVs, dBV, which is decibel with the reference. It's a decibel measurement with a reference to 1 volt, and it's RMS. Okay? 1 volt RMS. So total harmonic distortion expressed in decibels, not dBV, not dBm, it's just decibels. Here's the formula. It's going to be 20 log over the total harmonic distortion, which we can calculate here, divided by 100, and that's going to give us the decibel value with a reference to the fundamental frequency. We just want to know how much dirt our waveform contains. And this distortion number, this number here, tells us. We're going to call that, for our purposes, as Formula 2. Now, when we are dealing with our lab's oscilloscopes, here's the challenge that we are presented with, because we have those values given to us in dBVs. So the formula shows power. What do we do? How do we calculate the THD based on FFT display that we get, which is giving us the numbers in dBVs? All right, so I wrote here, consider Formula 1, which is this one right here. We know that power equals V squared divided by the resistance, or in our case could be impedance. Doesn't matter. I mean, it does, but it doesn't in our case. And I'll tell you why as we go along. So V squared over R, that's the formula for power when we are calculating the either DC power or RMS power. We can apply the same formula when we get the RMS values. We call this thing formula 3. So when we substitute the P's with the V squares over R's or impedances into this formula here, we get something like this little tapeworm here. So we have that 100, we carry that on, and we just substitute all the P's with the V squared over R's. And so it is. So there's the first, sorry, there's the second harmonics voltage squared over R. Okay, because this is the voltage squared over R. There's the third harmonic dBV, or the voltage squared, and so on. Okay. Then we divide that by the V squared over R of the fundamental, and it translates into this here. And look, if we take that division line, so dividing by the denominator here, we can multiply it by the inverse denominator. So here it is. We just made this one upside down and multiplied it. And over here we have the common denominators, so we can just have it V2, 3, and whatever number divided by R times R divided by the fundamental frequency quantity. Those R's are going to cancel. And we have a formula like this. And we're talking about the voltages. And these are the voltages RMS. Well, we have the dBVs, but we still don't know what the V's are because the values that we get on our FFT display are in dBVs. We need to know what the V's are, RMS. Can we find what they are? Yes, we can, because the dBV is a number with a reference to 1 volt. So what did I write here? It is possible to calculate the harmonics RMS voltages that are given to us in dBV. The RMS voltages of each harmonic can be found because dBV is dB with a reference to 1 volt RMS. So what is the voltage? Well, here's the formula. The voltage in dBV equals 20 log base of 10. We can write it, or if we don't, that means it's base of 10 of the voltage RMS divided by, so that's what the dBV is. Therefore, we can rearrange that formula here. That voltage, as we rearrange this here, so here we get this here. Voltage in dBV divided by 20 equals log of voltage RMS over 1 volt. And if we keep rearranging things, the voltage RMS, which we want, equals 10 to the exponent of the dBV divided by 20. Okay? So when you're going to be asked to calculate total harmonic distortion, you're going to have to go through the long, extensive calculations. And I'm going to ask you to show everything beautifully on paper in a way that I don't have to decipher your thinking. Maybe I'll show you some example later on. So all of those, and just skip no step, just keep writing things, and you're going to need an extra piece of paper for that one. So each voltage needs to be calculated and entered in formula 5 here. So for every spike that you're going to have, that is the harmonic, you're going to calculate the voltage RMS of that, voltage RMS of that, voltage RMS of that. Then you're going to square that, square that, square that, add those, and you're going to calculate the voltage, actual voltage of the fundamental, square it, apply this formula, take a square root of that, multiply it by 100, and you're going to have the percentage of dirt that that waveform has based on what you have displayed on the FFT screen. Okay. Now, a couple questions here. What allowed us to remove the resistance of the impedance? Simple question, but maybe not. And here's the second question that follows the first one. It's a daisy-chained kind of a system here. How can we be certain that every R has the same value? Well, because when we have whatever the signal generator is connected through some sort of a amplifier, a signal, and it is going everything, that waveform and all the noise that is contained in there, it's across the same load. So for every single quantity that we're dealing with, we're going to have the same resistance or impedance value, and they just cancel out. Okay. I will, right after this, I'm going to make a PDF version of it, and I'm going to upload it into our thing. All right. You know the thing. Okay. Now, time for more bread and butter here. Module 3, information, comma, bandwidth and noise. All right, get yourself a coffee. I have my coffee here. Getting cool. All right. Information and bandwidth. Bandwidth defines the frequency range over which a system operates. If we have an audio system, we want to be operating within 20 to 20 kilohertz, because that's designed for human hearing range or human hearing bandwidth. If we have some other equipment that is supposed to receive signal from other equipment, it could be certain type of data, it could be certain type of carrier signal, then we need to make sure that the bandwidth that we allocate for the system falls within the information that we are trying to convey through that link, for example. Um, So bandwidth defines the frequency range over the our system operates. More bandwidth generally means that more information can be transferred. Yeah. If you have a coaxial cable that has a huge bandwidth, then over that coaxial cable, you can transfer many TV channels. If you have a category 5 cable, Cat 5e cable, then it will have certain bandwidth if we want to transfer an analog signal through that. Or you need to have enough bandwidth to transfer one channel at a time. But the bandwidth has to be enough for the information to be not distorted or not aliased. Okay? What's aliasing is if the resolution of, let's say, the monitor is not up to par, and if you want to transfer, or if you want to display a huge resolution picture on that monitor, then things are going to get pixelized. And that pixelization is aliasing. So the information might look not as it is. We'll talk about that later in our later lectures. Hartley's law stated that the amount of information transmitted is directly proportional to the bandwidth multiplied by the time duration of the transmission. We will cover that slightly later as we get to that the other stuff, aliasing and whatnot. So the information and bandwidth times time of the transmission. Well, an example of bandwidth is example of a bandwidth is in the range of frequencies occupied by voice communication on telephone circuits. There is approximately 300 to 2.7 kilohertz. This gives us occupied bandwidth of 2700 minus 300 or 2.4 kilohertz. And yeah, we will get into more detail with that one. The importance of occupied bandwidth. The occupied bandwidth is often called a spectrum, or the part of a spectrum used. In most developed countries, spectrum usage and allocation is tightly regulated. In Canada, which is where we are, Industry Canada regulates the spectrum usage. Spectrum is quite valuable, and owning a spectrum can be quite costly. You want to have certain bandwidth over the air, you might have to pay money for it. Spectrum coordination between co-located countries is required to prevent interference. If there is a radio station transmitting their channels on certain frequencies, certain carrier frequencies, for example, then whatever the adjacent country has another radio station, it is a good idea for that not to transmit, the other country not to transmit on the same frequencies, because we're going to have a signal interference. So countries talk to each other, say, hey, we're going to have from here to here, and you're going to have from here to here, and everybody's going to be happy. Our people are going to receive our channels, your people are going to receive your channels, and everything is going to be fine. So things are regulated compromised and talked over between different partners because the air has no borders. um, Between Canada and USA, there's a careful coordination to address this issue. Collocated countries often have similar spectrum allocations. Europe, for example. Why is this important? Which is basically what I just talked about. So there's no interference in channels, and so everybody is happy. Here is a radio spectrum allocations in Canada. You can Google that, or you can get this thing on this site right here, and you can zoom it a little bit more, and it shows all the frequencies for the radio frequencies spectrum, and what channels, what bandwidth is occupied by what type of a signal. So there could be radio channels, there would be AM channels, FM channels, TV channels. Well, not so much anymore, because the cell phone industry is, excuse me, the cell phone industry is so demanding that some of the frequencies that used to be occupied by the TV channels broadcasted over the air, then those are being given up on the account of the cell phone industry, for example. I remember a few years ago, maybe sometime 15, 20 years ago, I remember we had to, in the audio industry, we had to retune all the wireless microphones, or the wireless, well, the transmitters used in audio in the stage gear. We had to those had to be retuned, and that was a big mess. To different frequencies, because some of the cell phone industry already was putting up their towers, and if you were using a cell phone, if you're using a microphone on the stage during a concert, then some of the interference from nearby tower that would you be using the same carrier frequencies or similar ones would cause some quite annoying interference, and usually that would be in some sort of a really, really loud kind of unspecified noise, electrical noise, and that was not good. So some of the frequencies had to be relocated. So things are being regulated. Why? As we said before, so there's no interference, and so everybody happy. Okay. Measuring and regulating frequency spectrum. In order to regulate frequency spectrum usage, we need to be able to measure it. Okay. The battery is made out of butter. All right. Spectrum analyzer. Here's a device that can be used as called a spectrum analyzer, which is some form of FFT, but it has some more features related to measuring certain things in a more convenient way. Spectrum analyzer can be used to measure spectrum usage. Usage measurements can include voltage, over power, and the occupied bandwidth. Actual measurements will depend on the physical location for over-the-air broadcast. So the further you are from the antenna, you would expect the signal to be a little bit weaker, and so on. Some oscilloscopes have the FFT function, fast Fourier transform function, that can also provide this type of function, except that if you're not using a spectrum analyzer, if you're using an oscilloscope, then you have to do a lot of those calculations by yourself, right? So remember when I said here, where's that supplement here? At the end here. In order to help you comprehend the process, that's why I'm going to make you go through all those treacherous calculations, calculating the voltages from the dBVs and then adding them on and plugging them in. So be systematic and clear within your within your presentation. I was actually happy telling Mr. Juraj that I can see that you guys and gals are really, really systematic and consistent with presenting your calculations. And Mr. Juraj says, yes, they are. Okay, so thank you, Mr. Juraj, and thank you. for doing that. Keep up the good work. Okay. So to help you comprehend the process, you'll go through the lengthy calculation sequence. Now, a spectrum analyzer is a tool that can automatically calculate and display the results. So you can just see them on the screen. But if you're using the FFT function on your oscilloscope, then some of the you can still see things, but you have to do a lot of calculations by yourself. When we're looking at the waveform on a oscilloscope display, this is called the time domain, which I just explained at the beginning of the class. If we're using spectrum analyzer or Fourier function, the FFT, we are then looking at the signal on the frequency domain on the x-axis. Okay? And electromagnetic radiation types, there's so much happening in the air that I won't even begin to start describing. But we are dealing with a lot of stuff. We're dealing with the radiation from the power lines, from antennas, from the towers, television and radio stations, cell phones, microwave. We're dealing with some infrared and ultraviolet and so on, X-rays and gamma rays and whatnot. And this would be the frequency in hertz on the bottom here. So this one here, this image just shows basically that there's a lot happening in the air, and it's all mixed with each other, with each other and itself, and within itself. Fourier series and analysis. Periodic waveforms can be broken down into a series of sine and cosine functions, a multiple of fundamental frequency. So here is the, this is related to the supplement that I showed here. And more or less, it's a detailed summary of that and maybe take into some different types of details than the other stuff. So you're going to have that as well. So periodic waveforms can be broken into the series of sine waves and cosine waves. And remember that stuff that I showed you here. So here is the fundamental sine wave. And usually be those sine waves that are distorting things, reshaping the wave, because they all add, they all mix with each other. The first term is called the fundamental frequency, and the other terms, the terms are the content. Okay, so this here, first item, first term. So this will be the first item or first term. There's going to be the second harmonic, third harmonic, fourth harmonic, and so on. So that's what they mean by the terms. The first term is called the fundamental frequency, and the other terms are called harmonics. A pure sine wave only has fundamental frequency, but we already talked about that. But the other types of periodic waveforms include some harmonics. A square wave and has in theory an infinite number of harmonics. Right. Most natural sound include voice, nature, musical instruments have harmonics. That's what makes a violin sound like a violin, because its resonating box is resonating, all right, with certain frequencies more and with certain frequencies less. And it's going to have that signature of the frequency domain. There's the frequency, and here is the, let's say, dB of whatever the power of signal. So because the box is constructed a certain way, of course, when you are making a sound on one of the strings, you're going to have a pure sine wave with the fundamental frequency, and everything else is going to have different type of a signature. It's almost like a fingerprint. Every single one of us has a voice that nobody else has, and you will have the number of harmonics present, certain number of harmonics present, and arranged in a certain way, exactly certain way. That's how we can recognize one person's voice from another person's voice. That's how we can recognize that the sound is being played by the violin, not a trumpet, because trumpet would have different signature, and so on. Pure sine wave only has fundamental, but all the other types of periodic waveforms include harmonics, a square wave, most natural. Okay, square wave is made up of odd harmonics, which we just showed on the little simulation there, with most of the energy found in the lower order harmonics. And as you remember, the equation for the sine wave and angular velocity with reference to time, or that would give us an amplitude in the sine wave and phase shift. Then you can add those harmonics. Each of those are the harmonics. Plus other ones. Every single one, every single thing that makes any kind of noise on this planet will have its own signature, like a fingerprint. I'm not going to ask you to do a long calculation like that. However, if you need to do any kind of research further in the future, then here is what where you can find things. At least you know something like that exists, and if you need to, you can find that and go deeper into it. Now, I'm just going to stop for a sec and explain something. There's a difference between teaching adults and teaching children. Children, you just give them tasks and they are happy to do things because they are not questioning, they're just getting fascinated with whatever is happening. Teaching adults it takes a little bit different approach, because you need to explain to the adults why they are learning this. So I'm trying to treat you like adults because you are. So I just need to, because I'm giving you different concepts here, and you might not see why you're doing this, why you're learning this. Just treat it as the building blocks for something bigger. Okay. You will need that thing further down the road. And in order for you to be able to use that, you need to know some of the concepts. So you might not see why you're learning this at this moment, but trust me, you're going to need that later on. Okay. For your analysis, for your series and analysis, a square wave is made out of infinite number of odd harmonics, as we just showed. Image C. Where's image C? C. Here. See that? If you start adding the odd harmonics, things are going to look like a square. So image C has the first, which is the fundamental frequency, third, fifth, and so on. And the shape is going to look like this. To get the more accurate representation, image E has 51 harmonics. Image E. So see, 51, you keep adding those harmonics and things are going to get sharper and sharper as a square wave, as not so many harmonics being present in a certain way, certain proportions. For this reason, square waves are problematic in communication systems due to the very high bandwidth needed. You need to get a proper square wave. You need to be able to convey through whatever medium, link, or device. It has to have a huge bandwidth in order to get those, see, up to 51 harmonics. Those have to be able to get through and register in that waveform. So square waves, they do require a lot of bandwidth, a lot of high frequency content present in order to make things nice and sharp like this. If you pass that through a square waveform through a low pass filter, it's going to start rounding off the corners And if you put that through enough filtration, you're just going to get sine wave again, because all the high frequency content is going to be filtered out. Oh, this is a very important concept. Okay, so now you know. All right. Understanding bandwidth requires, understanding bandwidth requirements is critical to understanding communication systems. But equally important is noise. Right? Noise can be problematic sometimes, unless you are doing some sort of a sound synthesis on a synthesizer at home for the music purposes. Then sometimes you might want to add some noise in as part of your art. But when it comes to communications or telecommunications, noise can be problematic because some of the noise floor, which is the bottom, well, it's called a noise floor. Uh, it can contain a lot of frequencies that can be mistaken as a signal or can interfere with the signal. To the user, noise appears as static and can be very annoying. To a listener in voice or music systems. So sometimes you want noise as part of the sound creation. And sometimes if you want a microphone signal to be really, and we call it quiet, which would be a pure signal, noise free, then it's a problem if the noise exists. So that's when it comes to analog type of a signal. In data systems, noise can result in dropouts or complete loss of data system or data stream. So here, let's say we have analog system interference. Here's some sort of a signal that we are trying to transmit and receive. If there are other signals present, they're going to maybe cut in and add to the waveform, making distorted. And as here is an ear, okay? If it's a human ear is going to receive that noisy signal, you're still going to receive that. If this main signal is strong enough and the noise is strong enough to be annoying, you can still receive the information and you can discriminate that the main signal from the noise inside your brain. We have pretty complicated or complex system going in our head. It's called our brain. Or when it comes to display over if it's a TV channel, yeah, then you're going to see certain type of images, whatever, trees and so on, and something else is going to cut through, and maybe someone is going to start doing some cooking show over you watching the baseball game or something like that, and that cooking show fading in and out could be annoying, but you still can see what the score was. When it comes to digital signals are square waves, right, or spikes. That would be an ideal type. And the digital signal is divided by slots, time slots, and it's being transmitted. So first there's going to be start listening now kind of information. So the receiver is going to receive that, say start listening now, and it's going to have those slots. It's called the baud rate of the timed transmission. The receiver is going to listen the data receiver is going to listen at the same speed that the signal is being transmitted. So, and it's going to find where the ones were, where the zeros were, and so on based on that. And if things are synchronized in a way that the listener is listening at this with the same baud rate, at the same rate as the signal is being transmitted, then the ones and zeros can be received properly and the signal can be reproduced on the other side. If you have noise in the signal, then some of those ones and zeros can be interpreted or can be lost. You're going to get some completely different message, and to the point that the receiver is going to say, I don't know what that signal is, and I'm just going to shut down. So interference in digital systems can completely shut down the transmission, while interference in analog systems can be, well, annoying. Or sometimes if the other signal is strong enough, it could pry out the main signal and take over the space. And you're not going to see the channel that you want to see. You're going to see the cooking show. In data system, okay. Have you ever experienced a noise listening to AM or FM or television? Well, with AM, you're going to receive more noise because FM is going to be more quiet because it's different type of modulation, right? Noise affects both analog and digital transmissions, communication systems, both over the air or transmitted over the media, like fiber optics, or coaxial cable, or data cables. Some of them levels are attenuated with the distance, so the further you get away, the weaker the signal is, and they become more susceptible to noise because when the signal is weak, it goes further away, signal is being weak, and the antenna is trying to pick up the signal with the noise because if the signal is weak enough, it's going to be comparable to noise. The signal to noise ratio is going to be not in our favor. So noise affects both analog and digital transmission. However, there are different techniques that can be used to mitigate the effects, mitigate the effects of the noise, and one of them was what I showed you some time ago was the differential amplifier, the operational amplifier. Yeah, so that's one of the ways to remedy that. All right, noise types. There are two major categories of noise in communication systems. Noise can affect communication systems with all types of transmission, media, free space, twisted pair. Twisted pair is the data cables, fiber optics. So noise can be there. Some transmissions media are more susceptible to noise. Like, for example, fiber optics fiber optic cables. They transmit light signals, so they're not going to be so susceptible to electromagnetic interference. Although the light is electromagnetic waves itself, but they're so far from the regular electromagnetic waves that if there's a lightning storm somewhere or if a Volkswagen drives by, that is not going to affect the optical transmission. Right? Often we refer to interference as a source of noise, as it has a similar effect in some cases. Okay, it can prevent the communication system from working. Well, frequency jamming. So you can jam the frequency by introducing the same carrier strong enough to prevent a transmission, certain type of transmission. External noise caused by sources external to the communication systems. Internal noise caused by equipment within the communication systems. So external noise, let's say you are going to install data wires close to the fluorescent lights. And there's noise from the fluorescent lights or alarm system or fire alarm. Those are the biggest noise makers. The cables or a thermostat also, they create a lot of noise. So you try to keep away at least 1 foot from with data cables from any of those, or machinery, industrial machinery that employs motors and actuators and whatnot. that can also cause interference within the data line. So that would be the external sources of the noise. And internal noise caused by equipment within the communication system, it could be a low quality mixing board, or it could be lower quality of an amplifier, and it can introduce its own noise into the system. Right? We'll talk about that in the further slides. External noise, human-made noise. This is noise caused by electrical, electronic, mechanical. Okay, we just talked about that. Transformers, power line noise is also quite common. This also includes switching noise. Category of noise is usually less than 500 megahertz. Atmospheric noise caused by natural phenomena in the Earth's atmosphere. Lightning is the most common storm. When it's storming, then you can hear that in the AM radio. This noise is often heard on the AM radio and is often an indicator of a storms nearby. This type of noise is usually less than 20 megahertz. Space noise. This type of noise originates in outer space, and the two dominant sources are the sun and other stars. Noise from the sun is called a solar noise. This noise is usually between 8 megahertz and 1.5 gigahertz. Okay. The worst troublesome from external noise is human made. There are standards and limits that apply to many products. Like, for example, anything transmits noise. Anything electronic radiates. Your mouse radiates. Your keyboard radiates. Your monitor radiates. However, things are being regulated. If they're being sold on the market, they're being regulated to not exceed certain type of noise. Things that as consumers we don't think about, but when it comes to designing things, some of the instructions or some of the guidelines have to be followed. Internal noise. Components and circuits with communications equipment generate noise. Insensitive receivers, where the desired signal is at its lowest level. Let's say you are a shortwave amateur radio operator. Then you're going to receive some signal from far, far, far away. That signal can be mixed with the noise. Now, during the World War II, when most of the transmissions, radio transmissions, if not all, they were AM, amplitude modulation. So there would be maybe some servicemen on the ship, and they will listen to some radio, and within that transmission, listening to some music, there would be some sort of a Morse code fading in and out because somebody would be transmitting. So if there was a radio station operator, which they all knew Morse code at that time, through the music that is being heard, they could say, "Oh, that ship is talking to the other ship, and they need so and so." Right? So there will be situations like that. But where were we? So there'll be sensitive receivers, where like radio is one of those, where you're looking at the further away you get from the transmission source, you're going to have to be able to detect small signals in order to receive the transmission at all. Right? So noise, it's at its greatest effect since it will also be amplified in subsequent amplifier stages. So if there is a signal received and there's a noise, and if this thing is weak enough and it's comparable to the noise, then you're going to have some sort of a problem there. And it's hard to get rid of some of that stuff, okay? Is it possible to filter out this noise? Sometimes yes, sometimes no. Depends on the situation. Like, for example, when I showed you that differential amplifier with the balanced signal through the mic from the microphone, yes, it's pretty much possible to filter out almost all the noise with the help of an op amp. But if you are getting if you're receiving things from antenna, then the whole thing is already mixed in with the noise you can apply certain filters depending on the type of signal. So if it's just a voice you want to hear and there's some kind of a high frequency buzz, then yes, you can apply a filter to eliminate that and still be comfortable with hearing the voice. One of those common things would be those DSL filters. Um, in the early 2000s, for some time, there would be those when a DSL line, DSL stands for digital subscribers line, and the DSL signal would be superimposed onto a telephone line. So the telephone line could be used to receive voice phone calls. And at the same time, you could have the internet being transmitted, the DSL signal. But if you didn't apply the filter, if you picked up the phone, you would hear that annoying buzz, the internet buzz. So the filters would be applied either at the beginning stage of the entry point to the house. So the internet noise would be filtered out and sent to modem, straight to modem, and the rest of the signal would go to the rest of the house. Or you could apply individual filters on every phone for that. So yes, sometimes it is possible to filter noise depending on the type of signal. If those are far enough from each other, then yes, if you're trying to listen to hi-fi audio, then it's at a cost because you're filtering out noise, but some of the noise would be also with the filters, you'll be filtering out the intelligence content of the high frequencies. So the answer to this is yes and no. Yes or yes, but. Okay. Types of internal noise. Okay. Well, thermal noise is could be quite problematic. Now, the extreme thermal noise is something that's called a thermal runaway. It's called thermal runaway. Like, for example, if a transistor is just about to fail, if it's at its failing stages, it will be sensitive to temperature. So some of the transistors or transistors within the integrated circuits, they're going to give you some, it's quite easy to detect in audio systems. In other systems, you need some additional measurement equipment like oscilloscopes or whatnot. But in audio systems, it was easy to find out because you would hear it's just like something is frying, something like that, right? Then you would get in order to find out which part it is that is giving you problems. You could do two things. You could spray the little freezy, there's electronic. There are those things in the can that you can just cool down with this. It's a can with a straw, and you spray a little bit of a liquid that cools things down onto the part. And if that thing stops, then it's probably that transistor that is giving you problems. Now, with thermal vision cameras, you can see which part of the printed circuit board has unusual kind of activity when it comes to heat. So you can do that. But that's the extreme things. Under normal operation, if things are not failing, certain components, electronic components, will introduce their own noise. Like, for example, transistors, the BJT transistors would introduce more noise than the FETs, field effect transistors, because the electrons have to go through certain type of ions and bump into things in the solid state, solid state, in the transistor type. Then if it's a field effect, then you would, the FETs, MOSFETs, JFETs, then you would have less interference, physical interference for the electrons to interact with, or the current to interact with, okay? But every type of equipment has certain type of noise. Okay? Now, when it comes to the some of the noise, let's see, okay, and this noise on the broadband breadboard. Okay, let's say the most noticed in resistance the most noise noticed in resistance. And this noise is broadband in nature. Broadband means spread around greater amount of the bandwidth that is being used. And it's also called white noise. The power in the power in this generated noise is given by the noise power, Pn, noise power, right, is Kt times delta F. Okay. All right. K is the Boltzmann constant. And it's not going to derive that. I'm not even going to begin. Boltzmann was a person who actually introduced us to, well, he was playing with the effect of temperature on different materials. And he came up with a constant. It's 1.38 times 10 to the negative 23 joules per Kelvin degree in temperature. T is the resistor. So we're talking about resistors. It's the resistor temperature in Kelvin degrees. And the delta F is the system bandwidth. So it's the spread of the frequency that we're using, we're considering. Okay, so here is the formula for the power of the noise. Let's see here. No, I didn't skip anything. Since P equals E squared, because power can be also expressed in voltage squared by resistance, then we can rearrange things that here's the voltage of the noise in RMS values divided by 2 and squared, and then the whole thing divided by R. Then it's going to equal to that KT delta F. Right? And we got two formulas to deal with here. This one is the voltage, the noise voltage squared divided by 4, because that's when we arrange like where I'm going to get that. Then equals that here. Okay. And if you want to calculate that, we arrange the formula. So the voltage, the noise voltage, can be calculated by taking a square root of 4, the Boltzmann constant, times the temperature in kelvins over the frequency range. Okay, so different types of resistors have different noise levels, with wire wound being the best, and the carbon film, which we're using, are one of the worst. Well, they're cheap. Example, find the noise generated by 2 mega ohm resistor at 17 degrees Celsius over 1 megahertz bandwidth. Okay, so we have, what are we trying to find is the noise generated, which will be the voltage, RMS voltage. Here is the formula. Right? Now, at this temperature, I just have a little bit here, okay? Here's the constant that we're dealing with here, the Boltzmann constant, and it is 1.38. Hold on, I just, okay, it's 1.38 times 10 to the negative 23rd joules per Kelvin. Right? Now we have 17 degrees. We convert the 17 degrees Celsius into Kelvin, so we have 290 kelvins. Right? So the K times T, this times that, is going to give us that, and the 4KT is going to give us 1.6 to 1.602 whatever times 10 to the negative 20, and that's what we have here. That's the 4KT right here. Right? Then the only thing that we have to multiply by the R and the frequency range that we're dealing with. So one is the 2 mega ohms resistor, and here is, was that 1 megahertz bandwidth right here. Apply the numbers, so you're going to find that the noise level of the resistor that we're dealing with at 17 degrees Celsius is going to generate 179 microvolts RMS. Okay. So yeah, what do we have here? 1.6 here, and then taking a square root. That's why you have that the whole thing, this whole expression, raised to the power of 0.5, which is power of 1/2. All right, 1/2, one one half, 1/2, which is basically just taking a square root. And just to prove that, okay, 16, square root of 16 is 4. Okay? Or if you take 16 and raise it to the power of 1/2, you're going to get 4. Let's get something else here. That's the algebra math here. 4. Square root of 4 is going to be 2. Whoa, same thing. Okay, so that's this is where that 0.5 exponent comes from. Okay? What do we have here? Many wireless systems are required to operate with signals in the 1 to 10 microvolt range. I see that. There's a problem, eh? But that's across the 2 mega ohm resistor. This is just an example that we have. So a much lower input resistance or impedance is needed, because that lower resistance is going to give us lower. 2 mega ohms versus 50 ohms. 50 ohms is standard for many wireless products. In fact, the coaxial cables for telecommunications purposes, they come at 50 ohm impedance, or the characteristic impedance, which we talked about last week. Transistors exhibit shot noise resulting from the current flowing within the resistor. That's the shot noise. The current carriers do always take the same path, resulting in the shot noise. It's called shot noise. In addition to shot noise, there's also excess noise below 1 kilohertz caused by the surface defects in semiconductors. Also, that thing is referred as a pink noise. At the high frequencies, near the frequency limit of the device, there's also something that's called a transit noise. And that's all I'm going to say about this one here. These low and high frequency noise effects are not as important for most high frequency transistor applications, but in some cases they are important. Now we get to more building blocks. Signal to noise ratio. Well, signal to noise ratio, it's the signal power over the noise power ratio. And if you multiply that, well, if you just do that, you're going to get a fraction. Multiplied by 100, you're going to get that thing in percentage. Or if you want to get that thing in dB value, then you take because we're dealing with power, we're going to apply 10 log, and with a base of 10, or sometimes it's not being written here, but this here. If we're dealing with voltage, we'll be applying the 20 log, but we're dealing power to power. We're dealing with powers. Then here's the 10 that we apply. Okay. So if you want to describe the signal to noise ratio in decibels, then this is the formula that you're going to apply. Example here: if noise voltage across the resistor is 0.1 volt RMS, and the signal, so if noise is 0.1, signal is 1 volt RMS. Can you just divide voltages? No, you can't. You have to do this power thing, because power is voltage over resistance. And remember, we are dealing with a signal that goes through the same part, same resistor or same whatever device that has certain impedance. So that R or impedance is going to be the same if it goes through the same load. So V square over R, V square over R, that's the power, that's the power. See, power, power. That's going to give us 100, signal to noise ratio of 100. And if you want to describe express that in dBs, or decibels, then you apply this formula here. The signal to noise ratio of 100 is equal to the signal to noise ratio of 20 dBs, decibels. Not that since resistance is the same, the answer does not depend on the resistance. Oh, I wonder what the next slide is going to be. Noise figure. So first we're talking about noise, signal to noise ratio. Now we're going to talk about noise figure. As we look at the specific device or an amplifier stage, what is the interest? What is of interest is the amount of noise that is injected between the input and the output. So basically what we're talking about, a noise figure, is a figure that describes how much noise the amplifier actually adds just by passing the signal through it. And it is simple. Here, a noise figure in a logarithmic type of in decibels, or you don't have to have it in decibels. Noise figure could be as a fraction, or it could be in logarithms or decibels. Then if it's decibels, then you're going to have the 10 log of signal to noise ratio on the input divided by the signal to noise ratio on the output. Which is equal to 10 log of the noise ratio. And that's your noise figure here. Now, for an ideal device or amplifier, the noise ratio would be equal to 1. Because the same amount of noise that is present on the input divided by the same amount of noise that is on the output, if the amplifier did not introduce anything, so what got in passed through without adding more, then of course we're going to have a number 1 if you divide one by the other. Noise figure equals to 10 log 1, which would be 0 dB. 0 dB up or 1. Right? Noise figure would be 10 log of the signal to noise ratio. Right here. signal to noise ratio. And it makes sense because the noise figure would be 0 dB, which means nothing. I'm sorry, I hate to use the word nothing. No noise is being added by the amplifier by itself. That would be ideal amplifier. They do not exist. This is another good example of how dBs are convenient to represent communication circuit measurements. How much noise was added? 0 dB. That's all you have to know. What's this? What's the noise figure? 1. Oh, then you have to explain it to someone if someone doesn't, didn't review some of those things. Or, yes, I studied that 5 years ago. Oh, I have to review things. All right. Effects of the reactance on noise. Although practical inductors and capacitors have small resistance values, they are negligible. Generally, these effects on noise are very small and do not need to be even considered for the most part. The RC, LC, or the RLC networks do have an effect on noise as they limit the pass band, well, because they act as filters, right? So they can eliminate some of the noise, but it's a give and take. It's a double-edged sword because when you eliminate noise, you also can to be really careful not to eliminate some of the data with the noise. Is the equivalent bandwidth delta F equivalent frequency range. So equivalent bandwidth, and that's the expression, is used in the circuits with reactive components for noise calculations, and this is the formula. And I added that here for designing filters. What is the equivalent bandwidth? And here's that 3 dB. All right, we get the board. Here is famous axes here. Let's say this is a frequency, and this is the, well, voltage. Low pass filter, if there's a signal, a certain voltage, if there's no filter, then the frequency ideally should be straight line. Ideally. No, it never is, but okay. But if you apply a that's a resistor R, that's a capacitor C, and here is our output terminals right here. So of course, capacitor is conducting high frequency. The higher frequency, the capacitor conducts it easier. So the higher the frequencies are going to be dumped into the ground here, not going to be passed through. And the lower frequencies are going to get through better than the higher frequencies. So that's why this thing is called low pass filter. When you calculate the cutoff frequency by using this formula here, 1 over 2 pi RC, so you basically take certain value of the resistor, certain value of the capacitor, and you're going to calculate the cutoff frequency, let's say somewhere here, whatever the number is, it doesn't matter right now, it's just right here. And the characteristic of a low-pass filter is something like this. When it gets closer to the cutoff frequency, it's going to taper off like that. That's the, yeah. So when you have that, at this point, if you draw a line here and draw a line here, if it's power, then we're looking at 3 decibels with a reference to this point right here. You low at this frequency, the output of whatever the filter is going to be 3 decibels lower. That's the cutoff frequency. And over here, this will be the equivalent bandwidth of that filter. Yeah. That's all I'll explain here. Noise in cascaded stages. The first stage in an amplifier is usually the greatest contribution to the noise, as this is the stage where the input signal is the lowest, so everything gets amplified, and then once it's amplified, carried through, it's hard to get rid of it, right? We can calculate the noise using the Friis formula for multi-stage amplifiers, and here's the noise ratio, signal to noise ratio, one that's coming in there, plus that minus one, and the power gain ratio and so on. So you could just keep doing that tapeworm of a calculation. Here's the formula. Okay. Couple questions here, text questions, So go to the text and look some of those. We're going to tackle that next time we see each other. And there's an additional, are digital signals affected by noise, or does the noise only affect analog signals? Remember when I explained to you how the noise affects analog signals and how it affects digital signals? So that's your answer there. Sketch a 1 kilohertz square wave that passes through a 1.5 kilohertz low pass filter. Well, we're going to tackle that too. What's going to happen at the square wave? 1 kilohertz square wave that passes through 1.5 kilohertz low pass filter. Remember? Remember square wave here? Boom, boom. Okay. The more harmonics, the more odd harmonics are being present, the more sharp this edge is going to be. If you start cutting off some of the harmonics, then those edges are going to start tapering off because they're not going to have enough definition. It is just a matter of how much those things are going to taper off before that starts looking like a sine wave again, right? But you can do is in class when you have, or you can just go to that homework lab, just do a quick one, assemble of a filter by calculating the cutoff frequency, which would be what? 1.5 kilohertz. See how this thing is going to look. I would be curious if I were you. What does spectrum coordination mean? What would happen if two adjacent countries decided not to practice spectrum coordination? Who regulates the spectrum? Well, in Canada, that's easy here. In Canada, the spectrum is regulated by Industry Canada. And what would happen? There will be a lot of interference and there will be a lot of not happy people. Right? What's another name for thermal noise? Hmm? It's the type of, okay, hint. I just went back to kind of show you that it's in the notes. It has to do with the color noise, color of the noise. Okay? Of course, you can't see the noise, but we just call it by certain. Oh, there you go. Somebody said that. White noise. There you go. Philip, thank you. What frequencies do televisions in channel 17 use? Why is there a gap between channel 6 and 7? Eh, this question is becoming an obsolete question because some of the channels are being eliminated from the broadcast. So I'll leave that one with you. So you can just look at the tables of the channels. Now, as a hint, not really a hint, but something that so you know, 6 megahertz is the bandwidth for each channel. Each channel takes 6 megahertz of space. And within that 6 megahertz, there are different carriers. There's a luminance carrier containing the luminance. There's some synchronization poles on certain carrier within that bandwidth. There's a color information. There's a sound information. And there's some other stuff there. But that's for the most part. But then again, some of those are becoming a little bit more obsolete. Now, those here, we're going to tackle when we see each other next time. Because I'm beginning to think that as we keep going with this, I'm going to put you to sleep. And I'm going to say a lot of words, which you're going to receive with your ears, but you're going to stop registering right now. We have done for almost 1 hour and 45 minutes straight. So we're going to use that gap for our purpose to just have this thing sunk in, start reviewing some of the notes that already I'm posting, and I'm going to post these notes today. It's about within an hour, they're going to be posted. And we're going to start reviewing some of the knowledge or the information. It's not knowledge yet. What's the difference between information and knowledge? It's just like having a recipe to bake bread. You get the recipe to bake bread. Guarantee you, the first time what's going to come out of the oven is not going to be bread. And then you're going to try to improve on things, maybe find out other things, trial and error. And after third or fifth time, you're going to have bread. And now you have knowledge on how to make bread instead of just having information. Same thing with what we are doing here. Right? It's getting the information, and how much you're going to use it is going to be supported by the labs, and then you're going to possess certain type of knowledge up to a certain degree. And then when you get to work, if your work will have something to do with this type of information and knowledge that we're gaining here, then you're going to build on it. And if not, you're still going to have that on the back burner of your mind. And if you need to later on in the future, you will at least know where to look for specific type of information. Okay, that's it for today. Is the test going to be a multiple choice or open answer? It's going to be a combination of I'm going to give you some multiple choice. I'm going to give you some open answers, and I'm going to give you something to analyze and certain calculations. But we will deal with that during the review. Thank you for asking, anyways. Okay, cool. That's it, and I'll see you next time. It's been a blast.